Good afternoon, everyone. I'm Giorgio Veronesi, President of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for almost 9 years, and currently I'm in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects around the world with several assignments overseas. I'm very happy to be introducing this webinar on electrostatic charging of particles in flows, a very technical theme. Let me say something about the Spotlight Talk series. This is now our 5th year of this initiative, which started in 2020 to keep together the chemical engineering community during the COVID pandemic. The success of the previous editions convinced us to transform the Spotlight Talk in a regular feature of EFC program. So today we have 2 series in even years, spring and autumn, like this one, and 1 series spring in odd years, when we are holding the European Conference of Chemical Engineering in autumn. Let me take this opportunity to remind you that next year, 2025, the conference will be held in September in Lisbon, an event not to be missed. This fall, we have 13 of our working parties and sections, namely sustainability, mixing, electrochemical engineering, high pressure technology, food, loss prevention, agglomeration, multi-phase fluid flow, static electricity industry, this one, education, polymer reaction engineering, thermodynamics and transport properties, and early career chemical engineers, delivering over 2 weeks a short session of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The complete program of the Spotlight Talk is available on EFC website. EFC promotes scientific collaboration and supports the chemical engineering activities in 30 European countries, representing more than 100,000 chemical engineers in Europe. EFC working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFC activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. Before concluding, I would like to thank all the people who work hard inside the working parties, the sections, and the EFC in general for this initiative to happen and to be successful. And in particular, I would like to thank very much EFC Martine Pou. She is in charge of the scientific secretariat in Toulouse. She did most of the conceptual setting up and practical activities for all these Spotlight Talks. So many thanks, Martine. I thank you for your attention. I wish all the speakers and the attendees a fruitful and successful webinar. But before giving the floor to Pedro Llovera from the Polytechnic University of Valencia, chair of the Working Party on Static Electricity in Industry, to introduce the works, I would like to express to Pedro my deepest condolences for all the losses and sufferings that the city of Valencia had to endure for the recent floods. That let us think how important it is to take the necessary measures to face the dramatic effects of climate change. So thank you, and again, I wish you a successful webinar.
So thank you, Giorgio, for your introduction and for your kind words for Valencia. Thank you very much. Can you share the screen, Holger?
Yes.
So I am Pedro Llovera. I'm the chair of the Working Party Static Electricity in Industry of the EFCE. I am electrical engineering by training. I've been working on electrostatic properties of materials, electrostatic diagnostic of industry facilities, offices, commercial areas for now more than 20 years. I am a teacher at the Polytechnic University and a researcher at the Energy Technological Institute, ITE, in Valencia, Spain. I would like to thank EFCE again for this opportunity of organizing this webinar in this series of webinars, especially Mr. Giorgio Veronesi for his presence in this webinar. Of course, thanks again to Martin for his great effort in organizing the Spotlight Talks. And of course, thank you all for attending. We are happy to see that this attracts attention to many people, and we hope it will meet your expectation. Now, some few words about our working party. The Working Party Static Electricity Industry brings together many experts from Europe and some from countries outside Europe to promote the research activity and the knowledge diffusion on electrostatics in industry. Even if static electricity is a relatively well-known and old topic, it is not very present in many applications, and it's not always well understood. I would say that static electricity has at least two phases, risks and applications. We can found as risk damage to electronics, safety incidents or explosion. As application, we have materials, electrodes, and static charge applied for adhesive applications. We have also precipitators, electrospinning, electrospraying, electrohydrodynamic flow. So even in application in aerospace industry, and more recently high voltage direct current, energy distribution, and biology. You can find more information of our activity in our webpage. So next slide, please. And our LinkedIn group is very new LinkedIn group. So we encourage you to join us. We post some news and some information about our activity and electrostatic in general. Next slide. Of course, Giorgio has already spoke about this conference in next year. I will talk more about our conference. Next one, please. In Electrostatics 2025, our international conference on electrostatics will be held in Bologna in November 2025, organized by the University of Bologna, especially Professor Ernesto Salzano and Giorgio Veronesi, who are in the organizing committee. Okay, we can speak hours about Bologna and the nice town it is, but I'm not the best one to speak about this. But you can discover the town if you come to our conference. Next slide, please. As a remark, and the proceedings of the conference are published at the special issue of the Journal of Electrostatics. This is a collaboration now for more than 40 years. So even if it's November 2025, we ask for papers quite soon because we make a peer review process, which takes some months to have papers published before the conference. That has been a tradition. Now things have slightly changed because the proceedings are online, so we can have some modification of the dates and maybe some papers after the conference, but we wish to have all the papers reviewed before the conference. Call for abstract is now open until 21st December. This call for abstract has to be done through the webpage of the conference, but then that helps us to organize the conference. But then we will open the special issue of the Journal of Electrostatics. So if someone missed this call for abstract, they can directly send a paper for the special issue of the Journal of Electrostatics. Of course, you need to register to the conference to, in the end, have the paper published at the Journal of Electrostatics. But even if you don't have the abstract, you can also send the paper to this special issue. And lately, if there are papers that are not mature for journal but want to be published to the conference, then we have a shortest delay closer to the conference to send papers just for presenting at the conference, and with no, let's say, copyright problems, so they can be after the conference published in any journal, or if the paper is improved, or we will not keep the rights on this publication. Okay, so we have these third dates now: abstract, then papers. If you miss the abstract, you can send the paper, and if you have papers not to be present at the journal, you can still have a new deadline later on the year. Next slide, please. So contact information, you have the webpage and the email for getting information of the conference. And I hope we will attract people to this conference. We organize it every 4 years. And we are coordinated with another electrostatic conference organized by IOP, which is also every 4 years, but shifted 2 years from ours. So we have every 2 years a conference in Europe. And the next slide. We also have the conference of the Electrostatic Society of America, which is, I think, every year. We have the chance to have with us Pupak, so she will, after his talk, give more details about this conference. Now I will give the floor to Holger Grosshans, who organized scientifically this webinar. He is the head of analysis and simulation in explosion protection group at ETV in Germany, Physikalisch-Technische Bundesanstalt in Germany. They work on process safety, focusing on ignitions, electrostatic charging of flows, gas explosion, and large-scale plant explosion. So please, Holger.
Yes, thank you for the kind introduction. I think I first apologize for some internet connection problems, so I will switch on video, and I hope that this will improve it. Yeah, it's a great pleasure for me to chair the spotlight talk of the Working Party on Static Electricity in Industry of the title Electrostatic Charging of Particles in Flows. I think if I counted correctly, this is the 6th spotlight talk of our Working Party. I think there were 7 in total, and we took part in 7. And I'm very happy that we have more than 15 participants in the spotlight talk today. The aim is to build with the spotlight talks also a community on electrostatics. So please engage and ask questions to the speakers in the chat. So I'm very happy that we have 2 very renowned speakers in the field today. Professor Mojtaba Ghadiri of the School of Chemical and Process Engineering of the University of Leeds in the UK. And the second speaker will be Professor Pubak Marani from the Faculty of Engineering at the University of Ottawa in Canada. Before I introduce the speakers, I want to give a very short introduction in the field. So in this field, electrostatic charging of solids or of particles, we have excellent research that deals with fundamental charging physics. So to really understand how on a very small surface charge is transferred from one surface to the other surface. Like in this picture here, you see to the left, we speak about what happens on areas of the size of several micrometers. And yeah, this is very interesting research, but we in the Working Party, we focus on the relevance of electrostatics for industry. And the relevance of this type of research for the industry comes from scaling up from this very small scales in the fundamental research to real engineering applications. Like, to give one example, what you see here to the right from the field of explosion protection, what is kind of my research field. So when large masses of powders are fed into a silo, then during transport or during the feeding, these particles charge electrostatically. And then in the silo, we can have cone discharges. These are discharges of a very high energy, what you see in this picture to the left of the silo. And these cone discharges, they have such a high energy that they can ignite the powder and they can cause dust explosions. So in silos, actually quite frequently, we can see dust explosions. However, besides explosions, electrostatics has many more effects on chemical engineering. For example, and I give you 2 examples which are now related to the speakers today. The left one is on pharmaceutical particles. So when we disperse pharmaceutical particles, for example, in inhalers, then they also accumulate electrostatic charge. And that's, of course, important for the functionality of these inhalers, because if they have too much charge, they maybe stick inside the inhaler and they don't go out, or maybe they stick in the they don't come to the lungs of the patient, but they stick somewhere else. So that's a very important topic. Or This right figure that I show here, which is a figure of a paper of the group of Marani, when particles accumulate charge, then it leads to wall sheeting or wall fouling. This here are pneumatic conveying ducts where the particles form a layer in the inside, but Professor Marani, she focuses mainly on fluidized beds. So in fluidized beds, also wall sheeting and wall fouling cause high material and process losses. So in general, electrostatics in chemical engineering is responsible for process losses. Yeah, with that, I want to come to the first speaker of today. And again, I'm very happy that we were able to get such a top speaker for the Spotlight Talks today, Professor Mojtaba Ghadiri. He is a full professor at the University of Leeds. And his research group does research on a lot of topics related to particle technology, functional nanoparticles, tribology, and electrostatics. I think is also an important topic for his research group. He is, for example, the speaker, I hope this is the correct title, speaker of the EPRC SRC research project on triboelectrification. That's a big European research project on the charging of particles. He received over the years many awards for his contribution to particle technology. Just to name, last year he received the Geldart Medal, and 5 years ago he received in Japan the Kona Award. So once again, Mojtaba, thank you very much for giving a talk today, and I let you share your presentation now.
Okay. Right. Right. Can you see my screen?
Yes, we see your screen. Yeah, and now it's full screen. Perfect.
Wonderful. Great. Well, thank you very much, Holger, for your introduction. I also would like to thank the panel members for inviting me. Actually, I have benefited from these spotlight talks and webinars, and I particularly would like to thank Martin Poo for doing that. We've been following that. In fact, on the electrostatics, I have benefited from the presentations made previously. So it's been a great pleasure to be with you and give this presentation on the work that we've been doing past and present. You might be familiar with the report of Ed Merrow. I don't know whether you recall him. He published a report some 2 decades ago on problems of particle processing. And basically in that report, he showed that the commissioning, the time for commissioning and the time for getting to the full production capacity of a plant which handles and deals with particulate solids is significantly larger than those of gases and liquids, for the simple reason that you are all familiar with. We have particulate solids which have surfaces, and these present great difficulties. Instigated by the International Fine Particle Research Institute, Ed Merrow actually had a fresh look on the issues recently, some 2 years ago, and he's published actually his paper. And his conclusions are basically that processing of particulate solids continues to pose still grand challenges even now. And of course, we have witnessed great advances in particle characterization, instrumentation, and new developments in manufacturing of particulate solids. But in my experience with our industrial collaborators, one major issue is the triboelectrification in handling and processing of powders and grains. So I will have the pleasure of introducing to you the type of work that we've been doing over the years in this line of work. So the content of the talk is just give you a little bit of background and introduction. Then I will introduce the particle charge characterization techniques that we have developed over the years: single particle impact, shaking mill, and aerodynamic dispersion. Then I will introduce our new EPSRC grant on triboelectrification and latest developments on charge distribution measurement, and then the work on pneumatic conveying of surface treated glass beads, which in fact I have carried out in collaboration with Professor Veronesi's group. So on the triboelectrification, you are familiar with natural phenomena that I put the cat and the volcanoes here for you to entertain you. But overall, the collisional and sliding contacts of surfaces of solids are commonly associated with electrical charge transfer, and this leads to charge accumulation and is the source of problems that Holger pointed out in showing the silos and the problem associated with it. So insofar as our interest is concerned in industrial applications, as you know, handling and processing of particles causes problems and explosion hazards. So in here we have the two videos. On the left, you see a recirculatory loop which actually contains glass beads with perspex containers. And I don't know when, as at the top of the cyclone on the left, you might see discharges, and the same rig is actually shown in higher magnification on the right-hand video. And if you pay attention to the surface of the glass beads on the cyclone, you can see the electrical discharges. Of course, this is the material here is glass beads, and therefore there's no issue for explosion. But if it was, for example, flour, then probably we would have had explosion. So really, the problem that you see here is on handling of particulate solids is a serious issue in terms of electrostatic charges. So to give you some examples of triboelectrification and the problems that we experience, so we have strong adhesion to containing surfaces that impairs flowability and in extreme cases blocking of the pipe. Then we also have lumping and auto agglomeration of the particles, again due to charge accumulation. And this together with segregation, they can actually upset formulation. So if you are dealing with formulated powders containing many ingredients, then it's likely that the differences in charging of the components in the mixture can upset the balance of formulation. I have, for example, worked on antibiotics containing sodium carbonate, and the triboelectrification can actually offset the level of concentration of sodium carbonate and therefore the dissolution of antibiotics in water. I have also experienced filling up of spiral jet mills due to triboelectrification. So once we are milling organic materials which are highly chargeable, we've seen cases where the material goes in expected to be milled, but actually they just accumulate in the mill and they don't come out because they have gathered so much charge that they are just precipitating on the walls. So these are basically four types of problems, industrial problems due to triboelectrification. But in fact, we also have positive aspects, which are one of the example which is actually taking a lot of attention is triboelectric nanogenerators producing small currents by sliding friction, and the attention on that is actually growing exponentially. So In terms of influencing factors, there are so many factors in here. So we have material properties in terms of work function and surface roughness. We have mechanical force which affects the contact area, pressure and impact velocity. We have environment and, of course, temperature and relative humidity accountable for influencing triboelectric charging, and particle morphology, of course. Then you have particle size, shape, surface roughness, etc. So as you see, there are so many influencing factors, and it's almost impossible to actually do any experiment when we can take one aspect, vary that, and keep the rest constant. And that really causes complexity in analyzing the triboelectrification issues. So we have developed a number of tools for characterization in addressing this. And so I'm going to basically present what we've done in terms of single particle impact charging, shaking mill, aerodynamic dispersion. And more recently, as we are working on now, we are looking at measuring or characterizing the charge distribution on the particles as a result of triboelectric charging. So just to give you a little background on what we've done in the past on single particle impact charging, this was actually instigated by Dr. Kendall Pitt, then at Merck Sharp and Dome. He was aware of our work on impact attrition. And so he approached us to see whether we could actually study the triboelectric charging of particles by single impact. So I converted our single particle impact test rig to a impact charging measurement by equipping it with a Faraday cage, which is used for collection, and also a through-type Faraday cage, which measures the charge as the particles pass by. And in here, actually, the preamplifier that you see here was developed in collaboration with Professor Tatsushi Matsuyama in Soka University. So with this one, we actually could introduce the particle singly, measure the residual charges on the particle as go through the through-type Faraday cage, impact on the target, do a charge transfer to Earth, and then they end up in the Faraday cage in here on a sieve mesh, and we can measure the charge which is on the particle. So we could actually look at the charge balance between what comes in and what is moved to the digital oscilloscope, and based on that, see the charge transfer. So basically, with this, we studied the impact charging of a range of materials, and basically, you get this type of behavior if you plot the initial charge that we measure with the through type, and also the charge transfer, we call it impact charge. Then you get a family of lines, and these lines, of course, increase with impact velocity. So delta Q naught, which is the impact charge here, that at zero initial charge, that is a function of impact velocity, and in turn the function of surface area during contact. And what we find actually that there is on these lines, they all have an intercept with the initial charge, which we call it equilibrium charge, and that is the charge at which there is no charge transfer. And so therefore, this is an important function, property of the solid particle, and characterization of that is important because it is actually related to the contact potential difference and work function of the material. Delta Q naught is also, of course, also important because it reflects the mechanical deformation of the particle. So with delta Q naught and equilibrium charge, essentially, we can characterize charge transfer. And that's basically what we've done with single particle impact charging. And as you see here, this is the equilibrium charge. So we plot the equilibrium charge as a function of impact velocity, and as the impact charge is expected to be independent of impact velocity, here is the evidence. Ethyl cellulose, the charge is independent of velocity. The same applies to sugar granules, alpha lactose monohydrate, and aspirin. So in a way, characterization of that is important, and I advocate that we should have some way of characterizing the charging of particles in this way. I would like to draw your attention to this alpha lactose monohydrate, where the equilibrium is just -18, and aspirin is -40, because I want to use it later on for relating to other measurement techniques. So this method that we developed actually didn't find much industrial application because it was actually difficult to have it on an industrial sort of laboratory. It's a time-consuming way of doing it. So it was good for academia, but not for industrial application. So we moved on, adopted this shaking method where we could put the particles in a container and shake it using a Retsch mill. And then triboelectrification can take place by collision of the particles with the walls, and then this can be emptied into a Faraday cage for measurement of the charge. So this work was actually supported by Bristol Myers Squibb, and with that collaboration, we managed to characterize charging of a large number of active pharmaceutical ingredients and also excipients, which have been published in powder technology. Interestingly, excipients charge a lot less than active pharmaceutical ingredients, which charge both negatively and positively. And you see, they can really get charged very high. So here you have -323 nanocoulomb per gram for this material. And the key to these materials are actually given in the next slide. So in here, we evaluated a large number of APIs and excipients. And the material key notes here, these are you can find in the paper that we have published. But the point here is that the APIs can get really very high charge negatively or positively, and positively here, and that the level of charge is very high. However, this process has got two drawbacks. One drawback is that when the material gets charged to that high level, some of the powders don't come out of the container, and these powders in fact have a lot of charge on them. So the characterization of the charge per unit mass is in a way inadequate. Probably we have a higher level of charges. That's one problem. And the other problem is that the quantity, although we still use sort of gram range of material, but that gram mass is still probably too large for pharmaceutical developments where, for example, at the early stages of drug development, there is hardly any material for large-scale testing. So really the drive is to go for smaller quantities, particularly for materials which are not that widely available. And a good example is pharmaceutical material under development. So in collaboration with Malvern Pananalytical, we went to using Malvern disperser for the morphology G3. At the early stage of the device, the morphology G3, they had exploding foil. So they were putting powders in a little spool, and the exploding foil dispersed the powders, and that was used for particle size analysis, particle characterization. But we had adopted it for measuring the electrostatic charge on it. So we put that disperser, which is part of morphology G3, on top of a Faraday cage, and made a pressure pulse which exploded these foils, and that basically did triboelectric charging by the particles colliding with the containing walls and foils, and in that way they get triboelectric charge, and the charges are immediately measured in the Faraday cage. So there is really no charge leakage, and in that way you get the maximum charge level. However, later on, Malvern moved to this type of design for dispersion. They gave up the exploding foils, and the spool has got a number of openings, as you see here, and the powder is put in here, and then still the same. You apply a pressure pulse of varying magnitude, ranging between 0.5 bar G to 5 bar G. And in that way, particles are dispersed. And in our case, we are measuring the electrostatic charge as a result of that by a Faraday cage. And we got our coordinator at Malvern Analytical, Paul Kipax, who arranged for us to have spools of different materials, copper, stainless steel, brass, aluminium, and PTFE, so that we could actually test the powder in which we are interested against these materials to put it in a triboelectric series, if you like. So that was the type of developments that we've been working on ever since. And the dispersion causes a large number of collisions of the particles with the wall, and that's where you get the charge transfer. And my collaborators, Alberto Di Lorenzo, he actually did initially some CFD DEM work, and he showed that during this process of dispersion, the charges actually come to near the equilibrium charge. I'll show you that one in the next slide, a higher magnification of the same thing, where this is actually modeling, yeah? And they calculated the total charge as a function of dispersion time, because we are applying a pressure pulse, and the profile of the charge as a result of collision and getting out of the dispersion spool, you can see for 53 micron and 109 micron. And basically, what you see here is that the particles get charged to almost 80% of the equilibrium charge. And that is, in a way, what we are interested is in the equilibrium charge. And that is a useful way of, and quick way of characterizing the equilibrium charge, if you like. And by changing the type of spools that we have, we can get the charge as a function of the material in which it is contacting. So here we have a 53 micrometer glass beads, which is being dispersed, and you can see the differences in charging. The attraction of this method is that actually the quantity that you use is very small. So if you see these little cavities on the measuring lever, these are measuring volume here, you can have between 1 millimeter cube to up to 15 millimeter cube of the powder that you can put in the dispersion spool and measure. So really, that is a very advantage in using this method. And I'm pleased to say that about 3 of the pharmaceutical companies with whom we have been collaborating have adopted this technique for looking at their powders. Another advantage here is that we can, by reducing the number of particles, then get to a point where we can basically extrapolate to one particle. And then say that is the equilibrium charge for that one particle. So here, for example, for aspirin, we have the charge per number of particles, and in here we extrapolate to one particle charge, and it will give a Q of minus 44 picocoulomb. And this is the result for lactose, where charge, again, as a function of number of particles, extrapolated to one particle gives the charge of minus 19 picocoulomb. And these measurements surprisingly correlate nicely with the single particle test rig that we did earlier on, where we had the single particle impact test rig. Because if I have reproduced this slide, and you see that with the single particle impact testing, the equilibrium charge for aspirin is minus 40, and for alpha lactose monohydrate is minus 18, and that one is what we get here by extrapolation here. So in a way, it's indirect validation, if you like, of the extrapolation measurement that we have here. So this method it enables us to characterize the charge transfer of a given powder. But the problem we have in the long term is we want to have predictability. So, of course, we know triboelectrification has been studied extensively, and we know the charge transfer mechanism taking place by electron, ion, and material transfer. But the problem is that with the organic materials and non-metallic solids, the mechanism of charge transfer is actually not well understood. And I think Holger actually pointed out to that. So we cannot currently predict the charge transfer. And of course, the role of environmental humidity and temperature as to the complexity of this process. So with a number of colleagues, we put a proposal to our Engineering and Physical Sciences Research Council, saying that we want to study this aspect from the fundamentals, from the molecular scale right up to the large scale application. And it turned out that our proposal was successful with support of those colleagues who supported it. So we have Dr. Andrew Scott on density functional theory, Dr. Simon Connell on Kelvin probe force microscopy, Professor Jerry Heng at Imperial College on contact potential difference measurement and effect of humidity, Professor Mike Bryant on triboelectric nanogenerator, and Dr. Jha and Weipin and myself on looking at charge transfer, charge distribution measurement, and application. So we have a team of postdoctoral research fellows, James Middleton on DFT, Jamie Mannering on Kelvin probe force microscopy, Isha Bade on CPD measurement, Jamal Umer on triboelectric nanogenerator, and Weipin, my co-worker, on measurement of charge distribution. So we are actually also blessed with a number of national and international collaborators who are supporting us and helping us. So we have Professor Pupak Mehrani helping us on pneumatic conveying, Professor Tiago Burgo from Brazil on Kelvin probe force microscopy, Prof. Alberto Di Renzo from Calabria on modeling and charge transfer on circulating beds, in collaboration with Prof. Francesco Maio, again at the same place. We have Prof. Mikio Yoshida from Doshisha, Japan, helping us on DFT. Professor Tatsushi Matsuyama providing general consultation on charge transfer and charge transfer models. And I also have two colleagues at Leeds, Arash Rabbani, who is helping us with machine learning, and I present some of his work that he's helped us on that, and Joshua Armitage, who is working on triboelectric nanogenerator. So we have put 7 work packages together, and these 7 work packages deal with molecular and DFT modeling for understanding and predicting triboelectrification. That is with Andrew Scott and James Middleton. We have Kelvin probe force microscopy on single facets of crystals and polymers, and that is Simon Connell and Jamie Mannering. We have surface energy characterization of single crystals and CPD measurement of bulk crystals by Jerry Heng and Dr. Bade. And the exciting point here is that we measure the single particle work function by Simon Connell, and then on given facets. And the question is, how does that relate to bulk CPD measurement? So that's the challenge ahead of us, which we are addressing. Mike Bryant with Armitage and Umar, they are working on triboelectric nanogenerators, looking at the way contacts and materials influence the level of current going by sliding. And for work package 5, 6, and 7, I have Weipin, who's working with me, Muzamil Ali, who is an external collaborator and an industrial partner in here, Arash Rabbani and Ziadun Jha, myself, working on these 7 work packages. Now, I want to focus on what we are doing right now on the development of a new rig for looking at charge distribution measurement. So basically, charge distribution measurement is not something that is commonly done. And of course, we know that particles get charged to different levels during the process of triboelectrification. So it's really of great interest to be able to measure that charge distribution. Now, for very fine particles where the charge and aerodynamic drag are influential, that is respiratable particle size, for example, then in that case, there are a number of devices like eSpart or the electrical impactor, where they can measure the electrostatic charge as a function of particle size. But for particles which are larger than about 10 to 20 micron up to a few millimeter, there isn't really actually any device available on the market. So we thought maybe we should start working on developing this by following the type of charge classifying that it has been well established in the literature for larger particle sizes. So we want to measure the charge distribution, and the idea was we provide a two-dimensional flow of particles and then apply a transverse electric field. And this idea is not new really, but we disperse the particles at the top of the chamber, and on falling down, subjected to electric field, they will deposit in different places on the lower level. And the idea was that depending on their position of deposition, we can infer the electrostatic charge on the particle. So that was a sort of simple concept, which is, as I said, is not really new, but is actually giving us a lot of difficulty. So first of all, we need to design a two-dimensional system. And for this two-dimensional system, what we decided was to have a disperser, which also produces a two-dimensional flow, really, in a way similar to the concept of the dispersion unit of malware morphology, and to introduce into the chamber in such a way that the particles fall under gravity without being disturbed by the gas flow. We introduced this cyclone, which not only basically lines the particles to fall down in here, but also it brings the particles to the equilibrium charge. That's the concept. And then we apply the transverse electric field in order to deposit on different places. So that was basically the idea. We've done a lot of work before actually constructing the device, looking at computational fluid dynamics and Lagrangian particle tracking in order to see what happens to this separating classifying chamber. So we explored three designs because it turned out that the fluid influences the particles as they enter into the classifying chamber. But we have made some design, special designs here so that the particles fall down under gravity without being much disturbed by the fluid. The fluid changes direction and goes up in the cyclone. And as you see here in this CFD simulation, basically the fluid inside this chamber is essentially static, and that is no fluid penetrates into here to disturbing it. So we have looked at Lagrangian particle tracking to see what happens to particles as they fall into this chamber. So basically what we have here is that the impact location on the, well, I should show you the bottom wall. So we have the frequency of deposition as a function of impact location on the bottom of the chamber. And as you see here, there's a complex pattern of deposition, which implies that the particles are chaotic when they fall down because they have slightly different radial velocity as on the entrance to the column. So even if we use all the particles to have equilibrium charge, for example, for 50 micron particles, all the particles have the same charge, then for 50 micron, they deposit in a well-defined place. But if we look at the triboelectrification, then they have a distribution of deposition because probably they have different charge level. So that is for 50 micron particle. For 100 micron particle, you have this situation. For 200 micron particle, you have this situation here. And for 400 micron particle, unfortunately, they are overlapping. So in inferring what is the charge as a function of particle size, as you see, is not that straightforward. So we decided to get help from my colleague in computing, Arash Rabbani, to see whether he can use machine learning to see whether he can get some information on pattern of deposition and whether this pattern of deposition relates to the electrostatic charge, knowing that we can change the transverse electric field. So we can change the pattern of deposition as a function of the electric field that we apply. And therefore, in principle, we should be able to analyze the pattern and relate the pattern to particle charge and particle size. So that's basically what we've been doing using Lagrangian particle tracking for calculation. So 50 to 100 micron particles we have here, and 2,500 kilogram per meter cube particle density. And then we have done 1,000 particles in here, ranging from 50 to 75 micron. And as you see here, at 1.5 bar pressure, we have charge as a function of location on the way. So these are the Lagrangian particle tracking. And basically, as you see here, the pattern of deposition changes with particle size. So in a way, for example, if you pick up a given applied voltage, like 500 volt here, which relates to that, so particles of different charges basically deposit, some of them on the wall, some of them on the bottom side, distributed from there to there. Right here. So you have a pattern of deposition even for a single particle. And if you move on to, of course, a distribution of the particles, so we assume a Gaussian distribution of particle size. For 0.5 bar G, you can see that you have particles of different sizes depositing on the bottom side with different numbers. So you have a complex pattern which evolves on that. And this pattern can be analyzed by machine learning. So we have particle size, particle landing position, discharge pressure, potential difference we apply on the transverse electric field. And with machine learning, we want to see final particle charge. So we have a training of 185,000 particles with a normal distribution that we know what the charge we have put on it. And then we have a test sample of 37,000 particles, which are randomly selected, different from that, to see whether the system is predictive or not. And Arash has done a range of methods for neural network, decision tree, random forest, linear regression, and stacking ensemble. And a stacking ensemble actually gives the best correlation, 0.9959, between the charge that we measure or we calculate, estimate based on Lagrangian particle tracking, and the one that AI is coming up with particle diameter being obviously the largest particle size. So we have a very small error, but the error increases with particle size. Also, again, we have a small error, but decreasing with the location of the particle. So near the center of the chamber, you have a large error, but towards the wall, you have a smaller error. So basically, that is the experimental, the simulation part, and this is the actual design and the construction. It is complete, really, and that is now is going to be commissioned for working on the on measuring the charge distribution. So we are having our fingers crossed that it will work, but we'll see. We'll report maybe next time in a meeting in Bologna, maybe, hopefully. I'm running out of time, and so therefore I don't have much full time to actually present the work that we've done in collaboration with Professor Mehrani's team at Ottawa. But we took some surface treated glass beads, and my co-worker James Middleton went there and did some with Pupak's team, did some work on looking at triboelectric charging of the material. And the concept here was basically using surface-treated glass beads to see how they charge. So that is the experimental rig of Professor Mehrani. So the particles are put in a T-junction there and then applied a pressure at time 0 where they carry the particles, and then the particles go around the bend in a conveying line. And then you have this Faraday cage where the the charge is measured. So we've done this work in collaboration with her, with using nitrogen and air as the carrier material. And the system under study is basically soda lime glass, size range 200 to 400 micron. And then we have surface treated these, acid washing to make them highly hydrophilic. And then we have silanized them with the silanization group. So acid washing basically produces hydroxyl group on the surface, which is hydrophilic. And then we silanize the same material by a silane group, which we buy from Sigma Ultra, which is called Sigma Coat. And that produces a surface which is highly hydrophobic. And so we wanted to see whether what the level of charge on these two are going to be, and whether we can predict them. So at the moment, I have only the experimental results that we have obtained, and I should present those to you here. So we have specific charge as a function of gas velocity for air and nitrogen. And as you see here, the experiments with air are producing slightly larger value of charge as compared to nitrogen. That is surprising to me. Also, interestingly, there isn't much difference between acid washed and silanized. So the black one, the blue one are silanized, the red ones are acid washed, and there isn't really much difference between them for both cases of air and nitrogen. And again, this is surprising. So we are now going to be looking at aerodynamic dispersion and see how the aerodynamic dispersion can be correlated with this via the computational work using CFD and DEM. So in view of the time, I will not go through that because I have some presentation here for that, but I think the time does not allow there. But as I say here, we have used our aerodynamic dispersion to do the same thing. But it requires some time to describe the differences in the system. So I wouldn't go through those, but come to my conclusions in view of the time. And the conclusion, I should say that the more we delve in triboelectrification by using better defined systems, the less, I should say, I understand the mechanisms. Maybe others can understand it fine, and I will look forward to learning from them. But in my case, it seems that I'm understanding less. DFD analysis being done by James and Andrew, is shedding some light on the underlying mechanism, particularly is describing the role of humidity. So far we thought that humidity actually is increasing the conductivity of the surface and therefore the charges leak. But what they find is that presence of adsorbed water layer actually modifies the work function of the system. So it does not necessarily is influenced by conductivity, but rather work function. So we're having validation in progress at single particle level by Kelvin probe force microscopy, and at bulk level by CPD measurements at Imperial College. We are in the final stages of putting the rig together for characterizing charge transfer by sliding for triboelectric nanogenerators. Charge distribution on particles, I showed you the computational work, and we are hoping to actually do the experimental work also aided by machine learning. And measure charge transfer in pneumatic convey line and bulk shearing will be validated with the predicted charge transfer by CFD and DEM. And that provides, hopefully by the conclusion of program, a capability for diagnosing charging of powders. And finally, thank you very much for your attention.
Thank you very much, Mojtaba, for this very interesting talk. Of course, I know a lot about your past research, but it was great to get an update and to see what you did in the recent years. I liked especially your last conclusions, that the more you learn about triboelectrification, the less you understand it. Something I also feel very often. So now we have some time for questions. We have one question so far. I would be happy to receive more in the chat. I saw in previous Spotlight talks that people usually ask the questions not during the talk, but in the end. Here, actually, you can write questions in the chat whenever you want, and we collect them and ask in the end. So I'm not sure if you can see the question, but I will read it.
I can see it. Yeah, it says, I would like to ask you about the plot where you show impact charge versus initial charge. You show that the lines intersect at one point, the equilibrium charge. I was wondering about the effect of surface roughness on both impact charges and equilibrium charges. Do you think that increasing surface roughness would move the equilibrium charge, because at a given impact velocity, not all surface area is in contact due to increased roughness? That is actually a very good point in that, but I don't know the answer. The reason being that we have not played with modifying the surface roughness. So we worked, as I showed you, on sugar granules, aspirin, paracetamol, ethyl cellulose, and these have their own characteristic of surface roughness. And although I really showed here the trend of single line, I didn't show you the experimental results, because in the experimental results, there is scatter. And that scatter it points exactly to your point about surface roughness. Because when we use glass beads, which have less surface roughness, we have a very good trend, which the line is not, the data points are not scattered much. But when we use granular sugar, then we have such a wide scatter in the results. And actually, for something which is highly smooth, and Tatsushi Matsuyama has done that for his impact experiments, you can get really a very good line with very little scatter. So roughness does influence the charge transfer, and of course that is very difficult to calibrate. However, if you notice, or maybe I didn't show it, but in our case we have used for contact area, we have used elastoplastic deformation rather than elastic. The reason being that for the materials of interest, they are not elastic. They have surface roughness, and this surface roughness is deformed as a result of impact, and therefore the contact area is larger than a sphere, if you like, or sorry, is different from a sphere. It's actually smaller than a sphere because of the protuberances. So the contact area model is that which was developed experimentally by Professor Masuda and his team. So we are using an empirical correlation with contact area rather than using Hertz's equation. So I don't know whether I have answered your question okay or not.
Yeah, thank you very much for the answer. Actually, I think Simon asked this question because he has actually developed a numerical model for contact charging that includes the surface roughness. Right. Maybe it makes sense that if you could try out, if he can explain the scatter that you spoke about with his numerical model.
Yeah, wonderful. Thank you very much. I will look at his publications. I will be great. Yeah, and thank you for your comments. And then the other one is says having the meter of glass tube before the impact target gives you a particle pre-impact charge. How did you vary the impact charge? How did you experience without any pre-impact charge? Thank you for your question. So we put the particles in that's why it's the time-consuming experiment. We put a single particle in a container of different materials, like for example perspex, and we shook it. So the particles was charged to the level that we wanted, and then we open the container and drop the particle through the system. So it could have slide in contact with the wall, but nevertheless, it had an initial charge, which wasn't really controllable, but it was measurable with the through-type Faraday cage. So we modified that. Whether we used the zero charge, I can't remember. I don't know. Probably we did, but I really cannot remember. Oh, okay. Bilge online. Hi, hello, Bilge. Hi. So Bilge is asking, my question is similar to the one already asked. There are lots of parameters, humidity, roughness, particle size, etc. How do you design your charging experiments? Do you try to keep all the parameters constant and try to probe the effect of one? You are very experienced in this subject. Maybe you already know that some are not very much important than the others. You're absolutely right. Bilge, actually is difficult to just change one parameter. So the only thing we did was surface of glass beads. You can manipulate the surface by acid washing and salinization. So we would have the same material, but with different surface characteristics. And that was the idea of using these two systems. Now, glass beads, although they are spherical, but they are not 100% good quality spherical. They have surface protrusions, some rough particles in them, and it's very difficult for an engineering level of approach to have 100% fully spherical glass beads. So we have only played with surface treatment and also play with humidity. And with humidity, we are having great difficulty to bring the humidity to zero level in our glove box. So in a way, that humidity is playing some challenges for us. We've done some aerodynamic dispersion with surface treated glass beads, and it seems that small level of humidity is influencing the process. So we need to get to zero humidity to be 100% sure that we can compare our measurements with those that we carried out at Prof. Meironi's group. So we have Giorgio.
Yeah, I propose that we take this as a last question and then we proceed to the next.
Yes, yeah. So in your charge distribution measurement test rig, the particles first go through the cyclone and then enter the chamber. Will the cyclone modify the charge distribution? Absolutely. We are hoping that it does increase the charges and brings it to equilibrium charge. But of course, particles of different sizes would have different charge levels. So the idea is to get the charge distribution and particle size distribution both at the same time. Okay, and I stopped for that because we need to give floor to Pupak.
I think we have to conclude this webinar now. Pedro or Giorgio, if you want to say something, then interrupt me, please. Otherwise, I would conclude now. So once again, thank you very much.
Pedro, if you want to say something, just to thank, on my side, I would like to thank all the speakers and the organizers and the presenters, because I think it was very, very much interested, and we had a very high and constant number of participants, which is always a very important sign. So congratulations to everybody. Pedro, if you want to say something.
I will also want to thank everybody. I've seen that some people asked me to join the LinkedIn group during the talk, so I'm happy to meet them. And if you want to join the LinkedIn group, it's open for you. And also remember the conference next year, and that's all from my side. Thank you all the speakers.
Hope to see you in Lisbon or in Bologna with some tortellini also. Okay. Thank you, Holger, for your coordination. Very well done. Thanks.
Thank you.
Okay.
Goodbye.
Bye-bye. Thank you.
Thank you very much.